Hello and welcome to the Unit 10 podcast on Section 16.1. Today we're going to be talking about energy. I'm Mr. Sakaguchi,
And I'm Mr. Lin.
and here we go. Energy basically is the ability to do work or produce heat.
There are two main types of energy categorized as potential and kinetic energy. Potential energy is due to saving or stored energy, and that's due to the composition or location, position of a substance. Kinetic energy, on the other hand, is energy that results from motion. Things that are moving have kinetic energy.
And what we find is that systems in chemistry will have both chemical and potential energy. The law of conservation energy is very similar to the law of conservation of mass, where energy is neither created nor destroyed.
But you can convert it from one type to another. So, for instance, you can take chemical energy stored in your body to move a bowling ball and move it into a higher position, and now you've stored energy in that higher location.
And this is also known as the first law of thermodynamics. For us, potential energy is going to be stored in the bonds of our substances.
So that would be things like food, which go into our stomachs, and then we process that for living. Chemical potential energy is then released in a chemical reaction. So, like if you digest something, and they can also be used for work. So we take our digested food to release energy to do things like work. And it can also be used to maintain our body heat. So energy can be used for producing heat as well.
The units for measuring heat are as follows. We have calories, and this is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius.
Not to be confused with the food calorie or the capital C calorie or nutritional calorie, which is actually 1,000 regular calories.
Or a kilocalorie.
Right.
And then we have joules. This is the systematic unit of heat and energy. And 1 calorie equals 4.184 joules.
Right.
Converting energy units, I thought it would be nice to kind of have some examples of conversions. They're basically just going to be dimensional analysis. So we start with, if I have 256 joules, how many kilocalories is that? Well, I start with my given over 1. I know that for every 1 calorie, that's 4.184 joules, and notice how the joules cancel out. We have 1 kilocalorie for every 1,000 calories, so calories cancels, and then if we multiply across and divide, we end up with this many kilocalories.
Right. So we can use this process to find out how much energy is in, for instance, a fruit bar that has 100 that's labeled as having 142 calories, nutritional calories. So you have your 142 food calories, and we know that there are 1,000 regular calories per 1 nutritional calorie, and so you are able to cancel out the nutritional calorie unit, multiply across with just the numbers, and you get 142,000 normal calories.
And then for the last one, we have 86.5 kilojoules. How many kilocalories is that? We convert our kilojoules into joules. We know this from our basic metric stuff. And 1 calorie equals 4.184 joules. And 1 kilocalorie is 1,000 calories. You'll notice that all the units cancel except kilocalories. And we end up with this as our answer, 20.7. Specific heat. This is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree.
So also, every substance has a very specific variable and rate as to how quickly it absorbs heat, and that's used with the letter C. And one thing to keep in mind is that the lower the specific heat of a substance, the faster it's going to change its temperature per amount of energy. And then the higher the specific heat, the slower it will change its temperature.
To give you an idea of the effect of different specific heats, gold has a very low specific heat. Water, in comparison to gold, has a much higher specific heat. If we heat them with the same heating element for the same amount of time, notice the difference in temperature. So notice how the kilogram of gold heats up more quickly than the water does, and this is because of the higher specific heat of water, and it's able to absorb more energy before it goes up in temperature, whereas gold with a low specific heat goes up rapidly in temperature because it absorbs energy faster.
And this is why when you're cooking and you're boiling water, it feels like it's taking forever. It's because water retains a lot of energy. It takes a while for it to change temperature. Also realize that due to the fact that gold can absorb heat quickly, it also releases the heat quickly as well.
And there's some instances where that's advantageous. So, for instance, a lot of your cooking uh, pans and things like that are made of metals, and the idea is that they're able to transfer the heat from your burners through the metal to your food to cook it faster.
Right. And the advantage of water taking so long would be things like you can take a nice hot bath and the water will stay hot for a much longer time.
So, how do we calculate this kind of stuff? We can quantify and use specific heat for the following equation, where Q equals C times M times delta T, where Q is the heat, C is the specific heat, M is mass in grams of the substance, and delta T is change in temperature, where it's the final temperature minus the initial temperature.
Notice that the specific heat is not a value that you can calculate for. It's something sorry, it's something that's given to you on a table, and we will give that to you in problems as we do the homework and take tests.
Also notice that for water, the specific heat changes depending upon the state of matter, and we'll show some examples of using this equation. So let's say we have, we want to use specific heat to calculate energy or heat. Let's say we have 34.4 grams of ethanol, and the temperature change increases from 25 to 78.8 degrees Celsius. How much heat has been absorbed? C, you would either have to look up or you would be given the masses from the problem, and the delta T we can come up with and subtract to get the change in temperature.
Recently, we were just dealing with the gas laws, and I know we were working with kelvins, and you had to convert to kelvins. You do not have to do that for delta T's for thermochemistry, because a change in temperature in degrees Celsius is equal to the same amount of change in kelvin. So you don't have to do any conversion for that. It's just straightforward. You subtract between the initial and final temperatures.
So once we have identified and our variables, we go ahead and we can substitute and solve. So we find that this is the amount of energy absorbed by the ethanol.
It could be represented as joules. It can also be represented in this case as kilojoules. If we don't specify, just go ahead and give it to us in joules. But do be mindful of what kind of unit may be asked in the question.
Right. We can also use the same equation to calculate temperature using specific heat. It's a little bit more complicated. Let's say we had a 4.5 gram nugget of gold, and it absorbed this amount of energy. What would the final temperature be if the initial temperature was 25 degrees? We have our specific heat that we look up. We have our mass from the problem. We don't know what the final temperature is. That's what we're solving for. And we know that the initial temperature was 25 degrees, and we know that the heat absorbed was 276 joules. So again, we go ahead and we substitute and we solve. So 276 equals 0.129 times 4.5 times TF minus 25. And then it's just an algebra problem from there on out.
Right. Do realize with all these word problems, if you're not sure what the C is, look for a substance. I know some students previously have a hard time trying to figure out what goes with where for the variables. And if you get stuck on the C part, look for a substance. And then that substance will either have the C value given to you in the problem, but if it's not, then it's something you look up on a table.
And then what if we have to calculate specific heat itself? So let's say we had a 155 gram sample of something that we didn't know what it was. We heat it from 25 to 40 degrees Celsius, and in the process we know that it absorbed 56.96 joules. So what is the specific heat? In this case, we're solving for C. So we have our mass, we have our Q, we found our delta T, so we're just going to solve for C, and we substitute and solve.
Right, and this process is actually used to find out what an unknown substance is, because specific heats are unique to different substances. That's why it's called specific. Therefore, now that we know that it's 2.45 joules per gram Celsius, we can find out what substance this unknown is.
And that's it.